1 billion years ago, Central Australia hit a supervolcano no one expected, eruptions so vast they outclassed Yellowstone, yet left behind almost nothing on the surface. Its secret was not a plume from deep within the Earth, but runaway heat trapped inside the crust itself. Why did this change everything scientists thought they knew about how the planet works? Let's uncover what really powered the buried giant beneath the desert. Central Australia, more than 1,000 kilometers from the nearest ocean, holds a secret beneath its barren red deserts. The Talbot Sub-basin sits at the heart of the Musgrave Province, a vast geological region wedged between the North Australian Craton and the South Australian Craton. This is not a landscape shaped by recent forces, but the product of events that unfolded between 1,090 million and 1,040 million years ago, an era geologists call the Mesoproterozoic. During this ancient interval, the crust here was thin, weak, and hot, primed by hundreds of millions of years of tectonic compression and radioactive granite intrusions. Dr. Chris Kirkland, whose fieldwork and helicopter surveys first drew attention to the buried structures of the Talbot Sub-basin, describes the area as a geological crossroads, one where the evidence of Earth's most powerful volcanic episodes is hidden deep below today's surface. The boundaries of the Musgrave Province, mapped through decades of geological surveys, define the canvas for a story that stretches across both time and space, setting the stage for eruptions on a scale rarely matched in Earth's history. The numbers behind the Talbot Sub-basin push the imagination to its limits. Over 30 million years, this hidden supervolcano produced eruptions that each released more than 1,800 cubic kilometers of magma, enough to bury a city the size of Sydney under several kilometers of volcanic rock. The preserved volcanic pile in the Talbot region exceeds 22,000 cubic kilometers of rhyolite, stacked in layers up to 9 kilometers thick. These figures dwarf the largest known eruptions at Yellowstone and Taupo, and approach the scale of Toba, the Indonesian giant often cited as the planet's most catastrophic. Where most supervolcanoes erupt once or twice on a grand scale, Talbot's volcanic engine rumbled on for tens of millions of years, unleashing repeated outbursts of unimaginable force. The sheer persistence and magnitude of this system force a new question. What could possibly drive such a colossal, long-lived eruption cycle deep in the heart of an ancient continent? Crust-driven. No mantle plume ever rose beneath the Musgrave Province. Instead, the crust itself became the engine of the Talbot supervolcano. Radiogenic granites rich in uranium, thorium, and potassium steadily released heat for hundreds of millions of years. This slow, relentless warming baked the crust from within, driving temperatures well above 900 degrees Celsius, hot enough to melt rock and generate vast reservoirs of magma. Extreme conditions. Petrological studies of zircon crystals from Talbot rhyolites confirm these extreme conditions, with measured crystallization temperatures routinely exceeding the limits seen in classic supervolcanoes. Long fuse. The heat was not a sudden burst from deep within the planet, but a long fuse, set by the accumulation of radioactive decay and the lingering warmth of ancient mountain-building events. Runaway melting. When fresh magma from below finally intruded, it triggered runaway melting in this already primed crust, producing volatile-rich, high-temperature rhyolites. The result was a supervolcano powered entirely by the upper crust, a process that rewrote the textbook on how the largest eruptions on Earth can begin. Distinctive chemical fingerprints set the Talbot supervolcano apart from any other on Earth. Oxygen isotope ratios, especially the unusually low delta -18 oxygen values found in Talbot rhyolites, reveal a history of shallow magma chambers interacting with surface water. These values sometimes dip as low as -5 per mil, far below typical magmatic rocks, and point to repeated cycles of magma recycling and water rock exchange near the surface. The volcanic structures themselves reinforce this story. Layered through the subsurface, geologists have mapped a series of overlapping, nested calderas, each one the scar of a previous eruption, later buried and then collapsed again as new magma surged upward. This piggyback architecture, recorded in both core samples and geophysical surveys, shows a volcanic system constantly renewing itself, cannibalizing its own crust. Unlike classic supervolcanoes, there is no sign of a mantle plume track beneath Talbot, just a tangled record of surface-driven processes and relentless crustal melting. These rock signatures, both chemical and structural, provide the hard evidence for a supervolcano powered from above, not below. Circular patterns hidden beneath the desert floor first appeared in gravity and magnetic survey data, hinting at a colossal volcanic system buried deep below. These faint geophysical rings, mapped by the Geological Survey of Western Australia, match no known surface features. When drilling crews set up on the Talbot Ridge, their diamond drill bit cut through layer after layer of volcanic rock, including ignimbrite, rhyolite, and granophyre, confirming a continuous volcanic pile nearly 9 kilometers thick. The core samples, extracted after a grueling desert campaign, provided hard proof. The subsurface anomalies were the scars of ancient calderas, stacked and deformed by time, now revealed by both remote sensing and rock in hand. Controversy erupted as geologists clashed over the evidence. Conference minutes captured heated exchanges. Some argued for a hidden mantle plume, while others insisted on a crustal heat engine. Pressure mounted for transparency, prompting the release of proprietary data after a formal request. With the debate unresolved, the community proposed a new campaign: high-precision zircon dating using chemical abrasion isotope dilution, thermal ionization mass spectrometry, aiming to settle the timing and tempo of Talbot's eruptions once and for all. Today, geologists still debate what else hides beneath stable continents. The Talbot supervolcano proves Earth's greatest upheavals can leave almost no trace, reminding us that certainty in science is always temporary.